Across the vast dark emptiness of space, there are magnificent clouds. These are not clouds of water, like the ones we see in our sky. They are enormous clouds of gas and dust, stretching for light years. We call them nebulae, and they are the cosmic nurseries where stars are born. Inside these cold, dark expanses, something truly wonderful begins to happen. The universe is not perfectly smooth. Tiny clumps of matter exist, and they have gravity. This gravity, though incredibly weak at first, is persistent. It patiently pulls on the surrounding gas and dust, drawing it ever closer over millions of years. This is the first, gentle step in the creation of a star. As more and more material gathers, the clump grows denser and more massive. Its gravitational pull becomes stronger, accelerating the process. The cloud begins to collapse in on itself, a slow but unstoppable fall towards a common center. As the gas particles rush inwards, they collide with each other more frequently. This friction generates heat. What was once a cold, dark cloud now begins to glow with a faint, deep red light. This glowing core is not yet a star. It is a protostar, a star in the making. It is a baby star, still gathering mass from its parent nebula, growing hotter and brighter as gravity continues its relentless work. The protostar's core becomes a place of immense pressure and rising temperature. The inward crush of gravity is powerful, squeezing the hydrogen and helium atoms together with incredible force. The temperature climbs to millions of degrees Celsius. At this point, a remarkable transformation occurs. The conditions become so extreme that the very atoms themselves begin to change. Hydrogen nuclei, which are just single protons, are forced together so powerfully that they overcome their natural repulsion. They fuse to create helium, releasing a tremendous amount of energy in the process. This is nuclear fusion, the engine that will power the star for billions of years. With the ignition of nuclear fusion, the protostar is truly born. It becomes a main sequence star. The outward pressure created by the energy from fusion perfectly balances the inward pull of gravity. This creates a state of equilibrium, a stable balance that will last for the vast majority of the star's life. The star settles down, shining with a steady, brilliant light. It has emerged from the darkness of its nebula, a self-sustaining beacon in the cosmos. Every single star you see in the night sky, including our own sun, was born in this way, from the patient and powerful hand of gravity sculpting the raw material of the universe. For billions of years, a star like our sun will exist in a long and stable period known as the main sequence. This is the adulthood of a star. During this time, it is a reliable furnace, steadily converting hydrogen into helium in its core. The process is incredibly efficient. The star has an enormous reservoir of hydrogen fuel, and it consumes it at a steady rate. This balance between gravity trying to crush the star and the fusion pushing outwards is what defines its existence. It is a cosmic balancing act on a grand scale, and it allows for planets to form and, on at least one world we know of, for life to emerge and evolve. Our sun is a perfect example of a main sequence star. It has been shining steadily for about 4.6 billion years, and it is only about halfway through its hydrogen-burning phase. This stability is crucial. It has provided the Earth with a consistent source of energy, allowing for the development of complex ecosystems. The star's size, temperature, and color are all determined by its mass. Smaller, cooler stars are reddish and can burn for trillions of years. Our sun is a medium-sized yellow star. More massive stars are hotter, shining with a brilliant blue-white light, but they burn through their fuel much faster, living for only a few million years. The energy produced in the star's core doesn't escape immediately. It begins a long journey to the surface. A photon of light, a single particle of energy, is created in the core and then begins a random walk. It is absorbed and re-emitted by atoms countless times, bouncing around inside the star for what can be hundreds of thousands of years. Eventually, it reaches the surface and is free to travel across space. The light from our sun that warms your face today began its journey from the core long before human civilization existed. It is a tangible connection to the deep past, delivered to us every single day. So, for most of its life, the star is a model of consistency. It shines, it warms, and it holds its solar system together through its immense gravity. But this cannot last forever. The fuel source, hydrogen, is finite. In the star's core, the hydrogen is gradually being used up, converted into a growing ball of helium ash. When the hydrogen in the core runs out, the delicate balance between gravity and fusion is broken. The star's stable main sequence life comes to an end, and it must begin the next, more dramatic phase of its evolution. The quiet adulthood is over, and a turbulent old age is about to begin. When a star with a mass similar to our Sun exhausts the hydrogen fuel in its core, its life takes a dramatic turn. The nuclear fusion that held gravity at bay for billions of years ceases in the center. With the outward pressure gone, gravity wins the battle. The helium core begins to collapse under its own weight, becoming hotter and denser. This rising temperature ignites the remaining hydrogen in a shell surrounding the core. This shell-burning phase produces even more energy than before. The star's outer layers swell up enormously, expanding outwards like a giant balloon. The star transforms into a red giant. The star is now vastly larger than it was during its main sequence life. If our Sun became a red giant, its outer atmosphere would expand to engulf Mercury, Venus, and possibly even Earth. Despite producing more energy, its surface is now much larger, so the energy is spread out more thinly. This causes the surface temperature to cool, which is why the star shines with a reddish-orange hue. The star is bloated, unstable, and nearing the end of its life. It is in this phase that the star begins to create heavier elements. The intense heat and pressure in the collapsing core can become great enough to fuse helium into carbon and oxygen. This red giant phase is not stable. The star pulsates, its outer layers rhythmically expanding and contracting. With each pulse, it sheds vast clouds of gas and dust from its surface, blowing them away into space. This process creates some of the most beautiful objects in the cosmos, planetary nebulae. The name is a little misleading. They have nothing to do with planets. They are the glowing, intricate shells of a dying star's atmosphere, illuminated by the hot, exposed core left behind. These expanding clouds carry with them the new elements, like carbon and oxygen, that were forged inside the star. At the center of this beautiful, expanding cloud of gas is the star's remnant, a white dwarf. This is the collapsed core of the old star, an object about the size of the Earth, but with the mass of a sun. It is incredibly dense. A single teaspoon of white dwarf material would weigh several tons. It no longer produces new heat through fusion. It is simply a hot, glowing ember, slowly radiating away its leftover thermal energy over billions and billions of years. Eventually, it will cool down completely and become a cold, dark black dwarf, a dead star drifting silently through the cosmic graveyard. This is the quiet, gentle death awaiting stars like our Sun. The lives of massive stars are short and spectacular, and their deaths are the most violent events in the universe. A star more than 8 times the mass of our Sun burns through its fuel with incredible speed. When its core hydrogen is gone, it also swells into a giant, but it becomes a red supergiant. Its core is so massive that gravity can trigger a whole sequence of fusion reactions. After helium fuses into carbon, the carbon fuses into neon, then oxygen, silicon, and finally, iron. The star's interior becomes like an onion, with concentric shells of different elements, with the heaviest, iron, at the very core. Iron is a special kind of atomic ash. Fusing iron atoms does not release energy, it consumes it. When the core becomes pure iron, the star's energy production comes to a complete and sudden halt. In less than a second, the fundamental balance is shattered. With no outward pressure from fusion, gravity takes over with catastrophic force. The iron core collapses in on itself at a fraction of the speed of light. The collapse is so rapid that it overshoots, and the material bounces off the incredibly dense center. This creates a powerful shockwave that blasts outwards through the star's outer layers. This rebound shockwave triggers a titanic explosion known as a supernova. For a few weeks, the single dying star can outshine its entire host galaxy, releasing more energy than our Sun will in its entire 10 billion-year lifetime. The explosion is so powerful that it creates temperatures and pressures far beyond anything the star could achieve in its life. It is in this cosmic crucible that all the elements heavier than iron are forged: gold, silver, platinum, uranium. The supernova then blasts these newly created elements, along with all the elements made during the star's life, far out into space, seeding the surrounding nebulae. What is left behind depends on the star's initial mass. For many massive stars, the collapsed core forms a neutron star. This is an object so dense that protons and electrons have been crushed together to form neutrons. A city-sized sphere, a neutron star has more mass than our Sun. For the most massive stars of all, gravity is completely unstoppable. The core collapses indefinitely, crushing matter out of existence and forming a singularity. This creates a black hole, an object with a gravitational pull so strong that nothing, not even light, can escape. These dramatic stellar deaths are not just endings, They are the violent, creative beginnings of everything that comes next.